Over the last couple of days, we've learned about 4 new terms. The first term that we talked about a couple of days ago was electric potential energy. And then, of course, after we looked at electric potential energy 2 days ago, we defined electric potential energy difference. Well, then we talked about electric potential. Sounds like almost the same thing as number 1, right? Electric potential energy, electric potential. They are almost the same thing, but not quite. And then, of course, the fourth one we talked about was electric potential difference. The first one, the most fundamental of the 4, is electric potential energy. Does anybody remember that definition that we used for electric potential energy 2 days ago, Wednesday, when we introduced this stuff? Pete? It's not the same thing as gravitational potential energy, but it's real analogous to it. Okay, if we think about the definition for gravitational potential energy, then the one for electric potential energy becomes pretty easy. Gravitational potential energy was the energy that's stored in a system of a couple of masses, 2 masses, right, a certain distance apart. Anybody tell me now what electric potential energy is? The energy stored not in a system of 2 masses, but rather a system of 2 charges, right, a certain distance apart. So the energy stored in a system of 2 charges, a certain distance apart. Does anybody know the symbol for electric potential energy? This one's easy, right? You got to get this one. EP, right? It's the same as the symbol for gravitational potential energy. Now the second definition, this is the easiest one in the world. The electric potential energy difference is going to be the difference between 2 electric potential energies. So if you've got a final electric potential energy and initial potential energy, then all you're going to do is subtract them. What's the symbol for electric potential energy difference going to be? Yeah, good. Delta EP. Now another way we could phrase that instead of potential energy difference might be potential energy change, or potential energy gain, or potential energy loss. Okay, they all mean the same thing. Now the third one, this is where it gets a little bit tricky. What about electric potential? What's the difference between potential and potential energy? Remember the Slurpee analogy we used yesterday? Hey, Danny and I are splitting a Slurpee. 300 calories in that Slurpee. The potential energy is 300 calories. The potential was 150 because it corresponds to the amount of calories per person, the amount of energy per person. Electric potential is not the total energy, but rather it's the energy per charge, per coulomb, right? What's the symbol for electric potential? V. The symbol is a capital V, and the equation for electric potential, if we think back to the way we defined it, it's the energy, the potential energy per unit charge. The 300 calories divided by the 2 people. Okay, the amount of energy per coulomb of charge. What would the units for this one be, by the way? We know that these are going to be joules, right? What would the units for electric potential be? Could be volts. Could be volts. What else could it be? Joules per coulomb, right? Good. Same thing, right? You don't have to do a conversion from volts to joules per coulomb. It's the exact same number. What about electric potential difference? It's delta V, and there's a couple ways that we can find that. The first way is using an equation that doesn't appear on our data sheet. It's the easy one. It's going to be VF minus VI. It doesn't appear on our data sheet, but it's easy. Right? If you've got the final and initial potential and you want to find the difference, then subtract them. Our grade 6er could do that, even without having any idea of what potential or potential difference really was. Okay, they could subtract those. What's the other way that we can find potential difference? Well, if potential is E over Q, then potential difference could also be delta E over Q. What would the units be for potential difference? Same as it is for potential, right? Volts or joules per coulomb. You got that? All right, there were 4 questions that you had to work on last night. 565, 2 of them. Any issues with those? They all went well? Good? And then we had 566, questions 1 and 2. I'm going to go over question number 2 just because we have to do a conversion from joules to electron volts there. Any issues with number 1? Okay, let's spend a couple minutes going over number 2 then. It says an electron moves between two positions with a potential difference of 4 times 10 to the 4 volts. A potential difference. It doesn't mention the word energy. Potential difference. No energy mentioned there. Clearly it's related to energy, but it doesn't mention the word. So are we dealing with an E or a V? We're dealing with a V, right? If it mentions the word energy, it's either going to be E or delta E. If it doesn't mention the word energy, it's going to be either V or delta V. Which is it this time, V or delta V? Potential difference. V or delta V? Delta V, good. So let's write that down. Delta V is 4 times 10 to the 4 volts. We want to find the electric potential energy gained. We're dealing with an E now, right? Either E or delta E. Which one is it going to be? Delta E because it's the energy gained or the potential energy difference. We're looking for delta E. And we're looking for the value in joules and electron volts. We'll worry about those units later on. By the way, we also know the charge and the mass of the electron if we need it. We just have to check our data sheet if you don't remember the numbers. We're going to say delta V is equal to delta E over Q. We're going to rearrange this. Becomes Q times delta V. Remember that form of that equation. Remember E is equal to Q times V. Electric potential energy, Q times electric potential. Okay, remember that. Because later on today, the topic we're going to do today, you're going to use this form of the equation often, Q times V. Okay, the rearranged form of it. The charge of the electron is 1.6 times 10 to the minus 19 coulombs, and the potential difference is 4 times 10 to the 4 volts. We multiply those two together, and we end up getting 6.40 times 10 to the negative 15. What units would we use? Maybe we can see here in our answer that it's joules, right? But pretend we didn't see that. Okay, how would we know that that's joules if it didn't say it in our answer there, okay? Because it's energy and because we used standard units, right, as we were calculating that energy. If you use standard units in an equation, what are you going to get out of it? Standard units. And the standard unit for energy is joules, all right? It's not what we call a fundamental unit, but it is a standard unit. All right, so we got that. We got it in joules. Now let's convert that to electron volts. To convert it to electron volts, I want you to take a look at your data sheet, the second page. On the left-hand side, about halfway down, you're going to see this. 1.0 electron volts equals 1.60 times 10 to the minus 19 joules. And then I want you to set up a ratio to get the number of electron volts out of this question. We're going to say 1 electron volt equals or over 1.6 times 10 to the minus 19 joules. So all we're doing is kind of getting rid of the equals with a division sign. That's equal to X electron volts over 6.40 times 10 to the negative 15 joules. So 1 to 1.6 is the same as X to 6.4. If we get the value of X, then we've got the number of electron volts for 6.4 joules. Solve for X, it works out to be 4.00 times 10 to the 4. Is it a coincidence that it's the same value as the electric potential difference here? The exact same value. Coincidence? Not really. Kind of, but not really. It's not a coincidence because of the way that we define an electron volt. And because we're using an electron in this question, the electron volts will be the same as the potential difference each and every time. But if we're using something other than an electron or a proton, something with a charge of 3.2 times 10 to the minus 19, they wouldn't work out to be the same value. So be able to convert from joules to electron volts, because it's not always going to be the same as the electric potential difference. You got that? How do we do the conversion? Set up a ratio. Okay, 1 to 1.6, that left side is always going to look the same, equals x to 6.4. Good? All right. I want to draw two pictures on the board here right now. First picture is going to be one that you're going to recognize from Physics 20. Remember these questions? You got a roller coaster at the top of a 10-meter high hill. It rolls down this hill and gets to the bottom. It's moving a certain speed when it gets to the bottom. Remember those? How did you solve that question? How did you analyze that question? Sorry? Yeah, it's an energy thing, right? It's a kinetic energy, potential energy thing. The way that I like to say it is EI equals EF. The initial energy equals the final energy. It's conservation of energy, right? The total energy remains constant. The initial energy, therefore, has to equal the final energy. Now, let me ask a couple questions about this. What kind of energy does this car have when it's sitting there waiting to go at the top of the hill? It's got potential energy, and it's gravitational potential, right? So it's going to be mgh. Does it have anything else at the top of the hill? Zero kinetic because it's not moving, right? Kinetic is dependent upon speed, and it's at rest, so there's no kinetic. What about when it reaches the bottom of the hill? Does it still have potential? The potential is its ability to fall to the bottom of the hill. It's already at the bottom of the hill. It has no ability to fall to the bottom of the hill when it's already there. Look, if you've got no height, you've got no potential. Does it have kinetic? It does, so we're going to say it's 1/2 mvf squared. You guys remember this? Is it ringing a bell, at least, from Physics 20? Let's change our picture a little bit here now. Let's have two parallel charged plates. One's positive, one's negative. Let's put a positive charge in there, right beside the positive plate. Let's give it an initial speed of 0, so it's just sitting there. What's going to happen to that car when it's left at the top of the hill? It's going to roll down the hill, right? What's going to happen to this charge as it's left there right next to the positive plate? It's going to roll down the hill, right? It's going to go towards the bottom plate. The gravitational field causes the car to go down the hill. The electric field causes the positive to go to the negative plate. We're going to analyze this question in the same way as we analyzed the car going down the hill. What kind of energy does this positive charge have when it's at the beginning here, before it starts moving? It's got potential. Right? It's not gravitational potential, though, because it's not gravity that's going to cause it to go towards the negative plate. It's electric potential. Okay? The electric potential we saw a few minutes ago was QV. Remember, E is equal to Q times Z? Remember I said, remember this form of the equation because you're going to use it often today? Electric potential is QV. What kind does it have when it reaches the other plate? It's moving, right? So it's got kinetic. And kinetic energy is kinetic energy. It doesn't matter whether we're talking about a car or whether we're talking about a proton or an alpha particle. Kinetic energy is kinetic energy, 1/2 mv squared. These two problems are really the same problem, right? Except that gravitational potential energy has been substituted for electric potential energy. mgh gets subbed for QV. I am not very good at visualizing electrons or protons or alpha particles moving through electric fields. I can't see that. That's abstract. I can deal with it, but I can't see it in my mind. I can see cars going down hills in my mind. I can picture that very clearly. Physics is easier for me if I have a way of visualizing something, if I can see it. So what I do when I come across a question like this where I got a charged particle speeding up, this is really what's happening here, right, is the charged particle is speeding up. When I have a charged particle speeding up, I picture it as a car going down the hill. I visualize the car going down the hill. And I ask myself, okay, what kind of energy does the car have at the top of the hill? Oh, mgh? Okay, perfect. I'm just going to sub mgh for QV. What kind of energy does the car have when it reaches the bottom? Oh, it's moving. It's got kinetic energy. Okay, well then the alpha particle would have kinetic energy at the end of it as well. Picture, literally, picture in your mind the car going down the hill whenever you have a charged particle speeding up, and solve it as the car going down the hill. Do this solution for the charged particle, but then just replace MGH with QV. Everywhere where you see MGH, replace it with QV. You got that? Well, let's up the ante a little bit here. Let's give it an initial velocity of 10 meters per second. What kind of energy does this car have now at the top of this hill? Kinetic, is that it? And potential, because it's still got a height, right? That hasn't changed. But it's now got kinetic energy as well. So we add 1F mvi squared to that. The final energy is still going to be the same. Let's make this one 10 meters per second as well. What kind of energy does this charge have at the first plate? It's got kinetic and potential, right? It's got potential because it's got the ability to go to the other plate. It's got kinetic because it's moving. So we're going to replace that with 1F mvi squared. And that's still going to be equal to 1F mvf squared. The analogy still works. If you picture the car going down the hill, we can still solve the problem of the charge speeding up in the electric field, as long as we replace MGH with QV. Let's try another one. Let's make it even harder. This time, we don't want to find the speed at the bottom of the hill. This time, we want to find the speed halfway down the hill. The initial energy doesn't change. What's the final energy become? 1F mvf squared plus MGH, because there's a height. What did you say? Okay. So on the other side, what do we got? If we want to find the speed halfway across, it's going to be 1F mv squared plus QVF. Right? The final potential, right? Out of curiosity, what would HI be in this question? What would the initial height? This is easy, right? What's the initial height in this question? 10 meters, right? What's the final height if we're going halfway down the hill? 5 meters, right? Let's say our potential difference across this gap here is 10 volts. What's VI in this question? VI as in initial potential, not initial speed. What's big VI? 10 volts. What's big VF? 5 volts. We've gone halfway across. So it's the potential V that's analogous to the height. What some people kind of get mixed up with in this analogy is they start saying, oh, okay, we need the distance between the plates. No, we don't. That has no bearing on this whatsoever. The distance is irrelevant. Okay, that's not analogous to height. It's the height that drives the car down the hill. It's the potential difference that drives the charge from one plate to the other through the electric field. So it's potential that's analogous to height. Does that make sense? Okay, let's switch this diagram up just a little bit. This time we've got a car at the bottom of a hill moving at 10 meters per second as it starts going up the hill. Let's say that it barely reaches the top of the hill. When it gets there, it's moving at 0 meters per second because it's barely got there. It's just ready to come right back down. That's supposed to be an outline of the car, by the way, showing you that the car is not really there. But when you're really close, like I was, it looked like that. But from your perspective, maybe it didn't. Say the height is still 10 meters. What kind of energy does the car have initially? Kinetic energy. And of course, at the end, it's got potential energy, right? If it's at rest, it's got potential energy. Let's go this way again. Here we got our positive plate again. Here we got our negative plate. This time we're going to start with a negatively charged particle moving at 10 meters per second going this way. Can that negative charge go towards the positive charge? Does it want to, first of all? Does it want to go towards the positive? It's repelled by it, right? Sorry, does it want to go toward the negative, I should say? Does it want to go toward the negative? It doesn't want to go toward the negative because it's pushed away, right? But it can go toward the negative because it's got an initial speed. Just like this car doesn't want to go up the hill. Gravity's pulling it down. It doesn't want to go up, but it does because it's given an initial speed. So this electron or this negative particle, whatever it is, can go toward the positive plate. And if it's moving fast enough, it can actually make it to the negative plate. To the negative plate. Let's assume that it does make it to the negative plate, but that it barely makes it to the negative plate. So when it reaches that negative plate, it's moving at 0 meters per second. It stops when it reaches that negative plate. What kind of energy would you say this charge has in the beginning? Kinetic, because it's moving. What kind would it have at the end of the problem? Potential, but it's not MGH potential, it's QV potential, right? So here's what I want you to take away from this. Whenever you see, Joel, a charged particle speeding up, I want you every single time to think of it as a car going down a hill. Visualize it that way, see it that way in your mind, and solve it that way. Just replace MGH with QV. Every time you see a charged particle slowing down, I want you to think of it as the car going up the hill. Think of it that way. See it that way. Write down, solve the problem that way. And then just replace MGH with QV everywhere you see that. Does that make sense? Okay, there's a page here that kind of summarizes what I just said. Now, if you wrote down those pictures and wrote a couple little notes so that it would make sense to you later on, then just use your judgment on what you need to copy down there. You need something copied, though, so that, Monday, after it's been 3 days, you're still going to remember this stuff somewhat, okay? This next page basically just says, look, we're solving it, we're dealing with it as a conservation of energy problem like we did in Physics 20, but we're subbing in QV whenever we see MGH. Okay? This time, we're dealing with potential energy that's electric potential instead of gravitational potential. Otherwise, it's exactly the same. So treat it that way. I got one example that I want to do with you today. 11.10 on page 571. It says a pith ball. A pith ball? What's a pith ball? Well, no, not exactly, no. A pith ball is a ball made out of material from the inside of a plant. It's pith from the inside of a plant, and it's really, really light. And the reason that's used sometimes in electrostatics experiments is because it's so light, it doesn't require very much force to move it. So you can notice forces without needing a very big force. Right? Light things accelerate quicker than heavy things. So let's use something that's really, really light, like this pith ball, and we're going to notice more of an effect of it, because it doesn't need so much of a force to notice the effect. This pith ball with a mass of 2.4 times 10 to the negative 4 kilograms, with a positive charge of 1.2 times 10 to the negative 8 coulombs, initially at rest at position A. Okay, here's position A. It's initially at rest here. VI is equal to 0 meters per second. At this location, it has 3.0 times 10 to the negative 7 joules of potential energy. When it's released, the ball accelerates toward the larger charge. So here's the larger charge. When you release a car at the top of a hill, it accelerates towards the bottom of the hill. This would be the top of the hill right here. This would be the bottom of the hill right here. So this pith ball is accelerating like the car accelerates toward the bottom of the hill. We're told partway down the hill the pith ball has a potential energy of 1.5 times 10 to the negative 6 joules. 10 to the negative 8 joules. That's 10 to the negative 8, actually, joules. It's kind of hard to make out there, but it should be 10 to the negative 8 joules. We want to find out what the speed of the ball is right here. This pith ball is speeding up. That's like a car going down a hill. If a car goes down a hill and it starts at rest, we know that it starts out with potential energy, MGH. Part way down the hill, the car has potential energy, but it also has kinetic energy. Now, because we're dealing with an electric charge here, this pith ball that has a charge, instead of a mass that's going down a hill, we're going to replace mgh with qv. We're going to replace mghf with qvf. And then we're going to sub in numbers and try to solve for vf, the final speed. Now, this question actually gives me a bit more of a break. We know the value of qv. We're told the initial value of the potential energy is 3 times 10 to the negative 7 joules. Okay, if we're not, it's not a big deal. Multiply q times v. But if you've already got E, then don't try multiplying anything. Just take the number and put it in. The final energy, the final potential energy, that is what is it? 1.5 times 10 to the negative 8 joules. We add to that, of course, 1/2 times 2.4 times 10 to the negative 4 times Vf squared. Let's pull out the calculator. And let's see what we can do with this. 3 times 10 to the negative 7, subtract 1.5 times 10 to the minus 8. Let's multiply that by 2. We've got to get rid of the half, so we multiply it by 2. Something's wrong there. Oops. 3 times 10 to the minus 7. Subtract 1.5 times 10 to the minus 8. Now let's multiply that by 2. Let's divide that by the mass. Divide it by 2.4 times 10 to the minus 4. And now let's square root that to get V. When we do, we get 4.9 times 10 to the minus 2. So Vf is 4.9 times 10 to the minus 2 meters per second. I don't know about you guys, but when I see that question right off the top, it looks confusing to me. Okay, we got a picture with charges in different places and energies and that, and then we got this question that talks about this pith ball accelerating, and I don't know about you guys, but a half an hour ago, this question would have seemed really hard. It seems still, when we read the question, kind of challenging. But now we have the ability to compare it to or relate it to the car going down the hill. If we do that, I think it simplifies it. What kind of energy does the car have at the top of the hill? What kind does it have halfway down the hill? Okay, let's do that. The question becomes, I think, a lot easier if we do it that way. All right, you have 2 questions for homework tonight. Saw that sigh. Oh, you thought you weren't getting any homework questions? Come on. 2 questions for homework tonight. You might even finish them in class here. You'll probably take a guess at what they are. Get the practice problems on page 571. On Monday, we will not do anything new. Tuesday, we have our unit test. Okay, Monday, nothing new. Monday is just, we'll do a little bit more of this, a few more extra questions of this, so we have a little bit more practice with it than just the 2 problems you're going to work on the weekend. And we'll spend some time reviewing, if you come with questions, that is. We'll spend some time reviewing. We should be good to go for Tuesday's test. All right? By the way, there is a worksheet. I can't remember the number. It's the last worksheet in the booklet that you have. Okay, I'm not assigning that as formal homework tonight. I don't want to do that. I want to be able to go over this first before I assign anything from that. But if you want a couple of extra practice questions, go ahead and try a couple of those questions on the worksheet this weekend. And I can help you with it Monday. Yeah, go ahead. All right, that's it for today, guys.